Of the numbers 2, 3, and 5, which are eigenvalues of the matrix shown here? Okay, so the way I'm going to go about this is just write out the formula that eigenvalues have to satisfy in terms of determinants of the matrix. And then because we're given the options that we have to choose from, 2, 3, and 5, we can just go ahead and substitute those into the polynomial and see which ones are roots. So I need to compute the determinant of this. I hope I remember the formula for determinant. Okay, I'll do a little bit of simplification here.
Sorry, something went wrong. Try again in a few seconds.
I'll do a little bit of simplification here before I start substituting values of lambda. In fact, maybe I will just expand the whole thing to make the substitutions a little bit easier later on. Okay. So let's just evaluate this at the three values 2, 3, and 5. I think I'm missing a squared here. So this looks like it works. That equals 0. So lambda equals 2 works. Okay, so lambda equals 3 does not appear to work. And let's try 5. Okay, so lambda is equal to 5 also appears to work. And this seems to be option C. Only 2 and 5. Yeah, I'm sure, as I got halfway through my computations, I realized there's probably a much easier way to do this. Is just start with the matrix itself, subtract one of these numbers, so 2, 3, or 5, subtract that from the diagonal, and then maybe from inspection, see whether the matrix is invertible or not. And you, of course, want the matrix to not be invertible for lambda to be an eigenvalue. But as I got really deep into these computations, I realized that I may as well just finish this with the approach that I'd originally taken. But yeah, in fact, just looking at this right away, if you let lambda be equal to 2, then these two rows become identical. And so instantly you know that lambda equals 2 is an eigenvalue. If I let lambda equal 5, then these two rows become identical. And we know that that will then be an eigenvalue. And so really it's only for lambda equals 3 that we need to figure out whether it's an eigenvalue or not. And I'm sure maybe I could have done some simple row operations to show that the matrix was invertible. But anyway, we got there in the end, probably longer than necessary. Thanks for watching.